Alright, this is video number 3. However, I made a mistake, a little mistake, but it's going to be, it'll turn out to be something significant a little later on. So go back to the previous page, page 6, and go find where I had, right here, it says atomic mass unit. I'll kind of blow this up a little bit so you can see where I'm at. It's at the bottom of the page on page 6. I said 1.7 as being the exchange value between these two. It's really 1.66, and doesn't seem real important, but you'll find out in a bit that it will be very important. Okay, hey, we just learned that when we assemble a nucleus, mass is destroyed, and when we disassemble a nucleus, mass is created. And we want to now actually run those calculations. We want to figure out how much mass is destroyed when I assemble a nucleus and how much mass is created when I disassemble, when I take apart a nucleus. And so we're going to actually calculate that in this particular video. You will need a calculator, so make sure you have a calculator ready to go. And here it is. We're going to take a look at nitrogen 15. Remember, it has 7 protons, 8 neutrons, for a total of what we call 15 baryons. Remember, 15 baryons is simply the number of neutrons and protons added together. Alright, so here it is. If you were to assemble, I'm reading right off the sheet right now, if you were to assemble a nitrogen 15 nucleus, you would need 7 protons and 8 neutrons. Calculate the total mass of the protons and neutrons before they are assembled into a nucleus. Show all your work below. Alright, so all we're going to do is grab, all we're going to do is we're going to take 7 protons and multiply it times the mass of each proton. And we had that on the previous video, which is actually located on page 6 of your notes. And the mass of one proton, let's see if I can look it up here and find it myself, is going to be 1.007825 U's. And so there's the first one. We also have 8 protons, 8 neutrons, and the mass of a neutron is on the previous sheet. Now, if you need to, don't hesitate. Stop the video, take the notes, because you're going to definitely need those as you move forward in this particular unit. All right, so I've got it set. I'll just go ahead and multiply these together and see what we actually get here. So I'm going to do 7 times 1.007825, and I get, scooch this out of the way a little bit, 7.054775 atomic mass units. Now I'm going to do the neutrons, so that's 8 times 1.008665, and on that one I get 8.06932 U's, okay, atomic mass units. And then all I want now is the total. So I want to add those together. So this would be just how much I have altogether. So I'll go ahead and take 7.054775 plus 8.06932. And there's 15. There it is. Alright, so let me record that. So that's 15.124095 U's. Okay, so what does that number mean? That's just the number of, it's a number that represents the total mass of all protons and all neutrons before you assemble them into the nucleus. Think of it this way. If you were to buy a puzzle and you weighed the puzzle before it was assembled, that would be the weight of the puzzle before it was assembled. It's all the pieces weighed together. Not assembled, but all the pieces together on one scale, okay, weighed. Okay, they're not assembled though, not into a picture yet. Okay, moving on. Next one, letter B. When nitrogen is assembled, its mass is 15.000108 U's. How much mass is destroyed, which we call the mass defect, when nitrogen 15 is assembled? Show all your work. Well, let's see if the numbers actually make sense. I mean, check them out. This is when it's assembled. This is when it's disassembled. and this is when it's assembled. And check it out. This number really is indeed bigger than this number. So when you put the pieces together, actually the mass of it shrinks. So as you assemble a nucleus, the mass shrinks. As you disassemble a nucleus, the mass increases. So we want the difference between these two numbers. All we have to do is subtract. So this one actually is pretty easy. You're just going to take 15.124095 U's, subtract off what it is after it's assembled. Subtract those two numbers. So 15.124095 minus 15.000108. Okay, and there's my number, and that is correct. So let's write that one down. 0.123987 U's. Okay, now what does that number mean? Well, this is the mass defect, so I'll put that over here. This is also the destroyed mass. This is the mass that's destroyed as you assemble the nucleus. You can also think of it as the mass that's created when you disassemble the nucleus. Remember, when you disassemble it, the mass goes up, and there's the mass. There's the additional mass. That's the amount the mass would go up if you disassemble it. It's also the mass that's destroyed when you assemble it. All right, so there's the first part. I'm sorry, there is part B. Now let's do part C. Use Einstein's equation to calculate the amount of energy in mega electron volts required to disassemble nitrogen-15. Show all work equations in units. All right, now here's our issue on this. If we start with E equals mc squared, this is the amount. This is the mass right here that is destroyed. It's going to be your mass defect, basically. And that number has to be, that mass has to be in kilograms. The problem is, I've got it right now in atomic mass units, U. I need this in kilograms. So I'm going to convert. And this is where we need that number that we changed at the beginning of the video. We need to use that number correctly now. So I'm just going to, on the side, right over here, just convert that number. 0.123987 U's. And I'm going to convert right here. So 1 U is 1.66 times 10 to the negative 27th kilograms. Again, I'll plug it into my calculator so you can see me do that. So 0.123987 times 1.66 times 10 to the minus 27th. And there it is. 2.0581842 times 10 to the 28th. I just want to make sure I got the numbers in there right. Yeah, it looks like I do. So let me record that number. 2.0581842 times 10 to the negative 28th, and that'll be in kilograms. All right, I'm going to check something real quick. Yes, I got it. All right, sweet. Okay, the next step is to go ahead and take that number, which is the amount of mass that's destroyed, which is this M. I'm just going to go ahead and dump it in there. So it's 2.0581842 times 10 to the negative 28th kilograms times the speed of light. Now I got to use this form of the speed of light because I need it in meters per second. And then I just multiply those together. So here's how I'll do that. Now, when I do this, I'm going to always start with the number that's in the parentheses. Get that one in first. There it is there. And then you can be fancy and square it, but I just simply just multiply it times itself. You'll actually have fewer problems that way if you do it. Just multiply by itself, then you're good. All right, and then we're going to multiply it times this big number here. So 2.05, actually it's not a big number, it's a very small number. Did I get that right? sometimes you just got to stop and double check to make sure you got it in there right, or else you're going to have a lot of problems as you move along. And I think I've got it. Yes. All right, I'm going to record that. So that's 1.85236,578 times 10 to the negative 11th, and that's joules. Now, I don't want my answer in joules. I want my answer in mega electron volts, and I have to do some conversions to make this happen. So here are the conversions. To go from joules into electron volts, you need a number that I haven't given you yet. And as a matter of fact, I'll write the number. You need to be able to see what I'm doing. I'm just going to write the number right up here so you have it. And it's going to be 1 electron volt is 1.6 times 10 to the negative 19th joules. All right. So we have right here 1.6 times 10 to the negative 19th joules is 1 electron volt. I'm going to go ahead and plug those numbers in. So 1.85236,578. Did I get that right? Yep. Times 10 to the minus 11th. And then I'm going to divide by 1.6 times 10 to the negative 19th. Alright, and yes, that's correct. So I'm going to go ahead and record that. So that's going to be 115772861.3, and that'll be now in electron volts. And then I'm going to convert from electron volts to mega electron volts, and we know that from the previous page that there are 1,000,000 electron volts in 1 mega electron volt. And so I'm just going to take the number that I have and divide by 1,000. And I get 115.77. And there it is. Okay, so this is the binding energy. So let me put this over here. Okay, this is the binding energy. What does that mean? That's the amount of energy needed to disassemble a nucleus. It's the amount of energy needed to disassemble a nucleus. Okay, or, yeah, that's probably the best way of saying it. Amount of energy needed to disassemble a nucleus. All right, and then the last one, the last question asks this. It says calculate the binding energy per nucleon. Now that's a little different. Okay, so we have to take our answer that we had above, which is 115.772861.3 mega electron volts, and we have to divide it by the number of nucleons in nitrogen. So if we go back to the top of the page, the number of nucleons in nitrogen 15 is 15. There it is, right there. That's the number of nucleons. So we'll divide by 15 nucleons. Here's my work, or here's my calculator so you can see it. So I'm going to take the number that's already in the calculator, which is right here, and divide it by 15. And if I did it right, yep, I get 7.718. And that's the number we're looking for. That is a very valuable number. And there it is. All right, there it is. Questions? See me if you have questions. Good luck on the next page.